Electrostatics, electric field due to uniformly charged infinite long wire. Here this is infinite long wire carrying charge plus Q. We imagine a cylinder as Gaussian surface and we are considering three faces S1, S1 circular portion, S3 lower circular portion and this S2 represents the curved portion. Now let's calculate the flux. So for this we write phi E equals closed integral. We consider all three faces S1. So here we consider three faces, that's why we are not writing closed integral. So S1 E times ds1 and cos theta 1. So theta 1 will be the angle between n cap and E. At this point it is 90 degrees. Then second surface S2 and then E area ds2 and cap, that is cos theta 2 plus third surface S3 E ds3 cos theta 3. Here theta 1 equal to theta 3 90 degree and theta 2 is 0. So this term and this term will vanish and we will be left with this term. So integration S2 times ds2. Now here ds2 means area represented by this cylinder. So we can say phi E equals E times integration of S2 ds2 and ds2 means curved surface area of the cylinder. So we write it E into CSA of cylinder. Here in this figure we can take this length as L and radius as small r. So curved surface area will be 2 pi E times 2 pi r and h is taken as L. So this is phi E. But we know that phi is given by Q upon epsilon naught. So this is equal to Q upon epsilon. From here we get E equal to Q divided by 2 pi epsilon naught R L. But if you remember, linear charge density lambda is given by Q upon L. So here Q upon L can be replaced by lambda. So E will be equal to lambda divided by 2 pi epsilon naught R, which is our required expression. Now let's consider next part. So here electric field due to uniformly charged infinite plane sheet. Here this is plane sheet. So as a Gaussian surface, we consider a cylinder. So these ends, the circular ends have area capital A. Electric field is directed like this. So N cap will be in the same direction. Here also N cap will be in this direction, means theta will be 0 degree. And on curved surface, if you consider any area, so N cap will be like this. But electric field will be like this. So theta will be 90 degrees. So we can say that contribution of flux due to curved surface area will be 0. Only contribution of flux will be due to these two circular ends. So we can write phi E equals E times area. Here we are applying formula phi equal to integration ds cos theta. Here theta is 0 degree, ds is A, so that is why phi equals to EA. So EA this side and EA this side. So 2EA, but phi equal to 2 upon epsilon naught equal to 2EA. Our concern is to get E. So E will be 1 by 2 upon epsilon naught times A. If you remember, surface charge density sigma is given by Q upon A. So we can replace this Q upon A by sigma. So we get electric field equal to 1 by 2 sigma upon epsilon naught, which is our answer. Now let's consider next case. Electric field due to two positively charged parallel sheets. So this is first parallel sheet. This is another. Sorry, this is first positively charged sheet. This is second positively charged sheet. They are kept parallel, and there are three regions that we are going to consider, and then we have to see what will be the net effect of due to these two sheets. So consider region one. In the region one, due to this sheet, electric field will be directed leftward, and due to this sheet also electric field will be directed leftward. So we say that E equal to minus sigma upon 2 epsilon naught minus sigma upon 2 epsilon naught, and that will give, if these densities are different, suppose we write here sigma 1, sigma 2, in that case these values will differ, otherwise we can take sigma also. So it will be like this. Similarly, if we consider this region, region 2, so in region 2, electric field due to first plate will be directed rightward, and due to this plate it will be directed leftward. So if we consider leftward as negative and the rightward as positive, so E will be equal to sigma 1 divided by 2 epsilon naught minus sigma 2 divided by 2 epsilon naught. Now consider region 3. So in region 3, due to first plate, electric field will be directed rightwards, and due to second plate also electric field will be directed rightward. So E will be sigma 1 upon 2 epsilon naught plus sigma 2 upon 2 epsilon naught. If we write sigma 1 and sigma 2 as same, so this will be doubled, this will become 0, and this will also get doubled. Now consider next case, electric field due to two parallel oppositely charged sheets. So electric field due to two parallel oppositely charged sheets. So here, this is positively charged sheet, this is negatively charged sheet. These are the surface charge densities. So again, we are going to consider three regions. So suppose region first. So in the region one, due to this sheet, electric field will be leftward, and due to this sheet, electric field will be rightward. So we can write here sigma 1, sigma 2, and in a special case, we can make sigma 1 and sigma 2 equal. So region 1, so it will be leftward, so minus sigma 1 divided by 2 epsilon naught. And from here, it will be rightward, so it will be sigma 2 divided by 2 epsilon naught. Now consider region 2. In region 2, electric field due to this sheet, means left sheet, will be towards right, and due to this sheet also it will be towards right. So we can say E will be equal to sigma 1 divided by 2 epsilon naught plus sigma 2 divided by 2 epsilon naught. Now let's consider region 3. So in region 3, due to first sheet, electric field will be directed rightwards, which we take as positive. So sigma 1 upon 2 epsilon naught, and due to this sheet, negatively charged sheet, it will be directed leftward, so it will be sigma 2 upon 2 epsilon naught. Now let's consider next thing, electric field due to uniformly charged thin spherical shell. So this is a thin spherical shell. Now suppose its radius is capital R. We consider Gaussian surface, is shown here, dotted circle, and the charge density of this spherical cell is sigma. Electric field will be directed outward. Now, so sigma is surface charge density. Now consider different cases. Suppose we consider a point P here, and then we find electric field for this. So we can say case 1, when small r is less than capital R. In that case, flux through Gaussian surface we have to find out. So phi E will be equal to Q upon epsilon naught, which is equal to EDS cos theta, here E into surface area, ES, and that will be E times 4 pi r square. But inside the spherical cell, electric field is 0. So ultimately, it will be 0 times 4 pi r square. So it has. So we have got case 1 when point P lies inside. This point has length. From here it is of length. Now we consider one point outside and one point on the surface. Suppose we consider second case when case 2 point lies on the surface. In that case, small r equal to capital R. So if small r equal to capital R, in that case, from here, E times 4 pi r square equal to 2 upon epsilon naught, or E equals Q upon 4 pi epsilon naught r square, but 4 pi r square can be taken as surface area. So Q upon area will give surface charge density. So we can write it sigma upon epsilon naught. Now, let's consider any point outside. Suppose point lies here. In that case, we will write the flux as case 3. So when point lies outside, charge enclosed will be Q. The total charge will be enclosed by it. So here we are considering point R is greater than R. So and surface area in that case will be S equal to 4 pi small r square. And then we again apply same formula, E times 4 pi small r square equal to Q upon epsilon naught, and we shift it towards right. So E will be equal to Q upon 4 pi epsilon naught times r square. Now we can plot the graph to show the electric field. So graph will look like this. Suppose this is spherical cell. So inside there is no electric field. When at this point, small r equal to capital R, here electric field is equal to is Q upon 4 pi epsilon naught capital R square. And after that, we know that when small r is greater than capital R, so E will be Q upon 4 pi epsilon naught small r square. That is, E decreases with the second power. So graph will look like this. It will be like this. This is electric field direction, and this is distance. Inside electric field will be 0, as I told you earlier. Now consider one question. In a certain region, the electric field is along the z-axis throughout. The magnitude of electric field increases in positive z direction at the rate 10 power 5 Newton per coulomb per meter. What are the force and torque experienced by the system? So let's consider the system. So here electric field increases in positive z direction. So we can write it del E, del means change, del E upon del Z is equal to 10 power 5 Newton Coulomb meter. And in other directions, del E upon del Y equal to del E upon del X would be 0. And here, dipole moment, direction of dipole is downward, means negative z direction. So we can say Pz is minus 10 power minus 7. Here value is missing. Dipole moment is given as Pz equal to 10 power minus 7 towards negative x-axis, negative z-axis. Sorry. Okay. So now Pz equal to 10 power minus 7. So now we can consider other directions. So Px and Py in non-uniform field, force acting on dipole is given by F equals Px del E upon del X plus Py del E upon del Y plus Pz del E upon del Z. We can put the values. So here Px is 0, Py is also 0. So first two terms will cancel out. So we will get third term as minus 10 power minus 7 times del E upon del Z is 10 power 5. So that will be minus 10 power minus 2. So this is net force. Now torque. Torque equal to P is sine theta. Direction of P is along positive z-axis. Direction of P is along negative z-axis. It means theta is 180 degree and sine 180 degree 0. Hence there is no part. Article 0. Now consider one more question. A charged particle minus 2 with mass m is given horizontal velocity vx. Find the vertical deflection at the edge of the plate. Here, this length is given as L and the separation between the plates is given as d. So let's consider horizontal motion first. So we can say L equal to, we are going to apply formula S equal to ut plus half at square. Along horizontal means along x-axis, acceleration is 0. So, and S is given as L, U is given as Vx. So, Vx into T. So, from here, we get T equal to L upon V. Now, along vertical or y-axis, velocity is 0, Vy is 0, but Ay is there. So let's see what is Ay. So we can apply formula 2E equal to ma, force on charge equal to mass into acceleration, from where we can get A equal to QE upon m. Now again we apply formula S equal to ut plus half at square. Here u will be 0. Along y-axis there is no velocity, and the time we have got as L upon Vx, and acceleration we have got as QE upon m. So as far as S is concerned, S is equal to D. So we write D equals 0 plus 1 by 2 QE upon m times t square, and we can put the value of t as L upon Vx. So we get D equal to 1 by 2 2e upon m times vx squared divided, sorry, L square divided by Vx square, which is our answer. Thank you for watching.